So we're going to continue our quick, hopefully, reintroduction for most of you to set theory with four basic set operations: union, intersection, complement, and difference. And these are the exact same things, like I said, most of you have probably seen before. The union of two sets is just everything in the two sets combined together into one superset, if you will. The intersection of two sets is everything two sets have in common. Right? Classic definitions, but I've added here definitions using our formal logical notation. So the union is the set of all x's such that x is in A or x is in B. And the intersection is the set of all x's such that x is in A and x is in B. So let's look at a few quick examples here, right? I've got A, B, C, D, and just you kind of, because it always sometimes can be a little unusual, I've thrown in the empty set there for D. So what is the union, for example, start with the union. What is the union of A and B? Well, kind of the brute force way to do this is you write out the elements of A and you write out the elements of B. And that works, but it's a bit of a mess, right? Because we never want to duplicate an element in a set. So if we cross off one of those first four, those are the ones that are duplicated. What's left is what I would call the union. And I'd like you to kind of notice something here. We're going to talk a little bit more about this when we start proving things. Notice that this set here is just a set B. Right? So why did that happen? Well, if you look a little closely again, you'll notice here that A is a subset of B. So we'll talk more about that relationship, like I said, in the next chapter when we start proving things. So how about intersections? How about if let's mix it up a little bit. How about if I said the intersection of A and C? Well, the intersection, I'm looking for things they have in common. So if I look at set C, it's got a -2. A doesn't, so that's not going to make it. C has a -1, but A doesn't, so that's not going to make it. And there's nothing left. There's nothing left to check here. So there is nothing in common. And that's fine. So our answer needs to be the set with nothing in it. Fine. That's the empty set. All right, so how about if we bring the empty set into the mix here? What is the union of A and D? Well, again, if I write out everything in A, that's 0, 1, 2, and 3. And then if I write out everything that's in the empty set, that's nothing. So there you go. That's our union. And how about if we look at the intersection? Well, what do they have in common? Well, look at A. It's a little easier, I think, if we look at A. 0 is not in D. 1 is not in D. Neither is 2 or 3. There is nothing that these two sets have in common, and the set with nothing in it is, again, the empty set. So we've got two more operations here: the difference of two sets and the complement of two sets. The difference of two sets, the difference of A and B, you take all of the elements of A, remove everything that's also in B, and what's left is the difference. Right? So I've got again the formal definition here. This is everything that is in A and isn't in B. And finally, we've got the complement. You remember the complement is everything not in the set. It's everything outside of the set. And to define this, we have to clearly define what constitutes outside. So you do need to bring another set into this. It's this set U. U is the so-called universal set. So U is all of the numbers or all of the things, right? There might be things other than numbers, but it's all of the things that we're going to be talking about. We cannot include anything in any sets that we're describing other than things that are in that universal set. So again, I've got the formal definition here, right? The complement of A is all x's that are not in A. So again, let's look at some examples here. You notice I have added a set. I've added a universal set for us here. So when we start trying to look at those complements, we know what numbers we have to base that on. So what would be, let's see, what would be A minus B. Well, sometimes when you're doing these and you have the roster notation, it's helpful to actually write the sets in there. So A is 0, 1, 2, and 3, and B is 0, 1, 2, 3, and 4. So my answer is going to be based on that A set. I'm going to look at that A list, cross off everything in B. What's left is my answer. So there's a 0 over here, so I'll cross off the 0. I'll cross off the 1 and the 2 and the 3. I cross off a 4 if there was 1 in there, but there isn't. So what's left? Well, nothing. Okay. That's a perfectly good answer. And our answer is the empty set. So let's see. What else can we try here? How about if we go the other way? What is B minus A? Well, now I'm going to do the same thing, and I'm going to go ahead and write it out again here. This is B, 0 up to 4, minus 0 up to 3. And the way I said it right there kind of gives you a hint what the answer is going to be. I'm going to cross off the 0, the 1, the 2, and the 3. 0, 1, 2, 3. What's left? Well, this time there is something left. Right? It's 4. And that's my answer. You notice, be sure you're using the set notation here, right? I'm putting square those curly braces around that to indicate that it is a set. All right, so how about, let's see, how about complements? Right, what is, let's say, the complement of A? Well, now this is kind of like a minus in a way. I'm going to take all of the things that are in A, cross them out of the universal set. So I'm going to cross out 0, 1, 2, and 3. What's left is the complement. -2, -1, 4, and 5. All right, well, I haven't brought the empty set into this yet, have I? Right, so let's bring the empty set in. What would be the complement of the empty set? Well, just kind of intuitively, the complement of the set that has nothing should be the set that has everything. And that's our universal set. Right? So the complement of D would be -1, -2, -1, 0, 1, 2, 3, 4, and 5. Or you could have shortcutted this and just said U. Right? It is perfectly okay to just use the letters. In the next lecture, we're going to look at some more definitions, some more operations, and this is the point where we may be starting to pass into information that some people may not have seen in their earlier mathematics career. We're going to talk about indexed sets, we're going to talk about partitions, and we're going to talk about what it means for sets to be mutually disjoint.